in that case, let's get started. No time to lose. So what did I say? I'd start by talking about the rank of a neural network, which is this measure of compressibility. So to keep things streamlined, I'm going to be considering a pretty simple model of neural networks where you have the sort of key quantity in the neural network model is the number of hidden units. So we can say let m, which is a natural number, be a number of hidden units. And then we're going to have a neural network with two inputs, m hidden units, and one output. So a neural network is like a graph. Looks like this. So we have two inputs. We have m hidden units. And then we have one output. And each of these connections between the layers has a weight parameter. And so you could describe this neural network with a parameter that tells you what all of the weight parameters are from the first input unit to the m hidden units, and then another m parameters for the second input to the m hidden units, and then a third lot of m parameters from the m hidden units to the one output. So a total of 3m weights. So I'm going to write W is a weight vector in R to the 3m. I'll briefly mention that the reason that I need two inputs is because that's going to put this into a two-dimensional problem. And if you have two or more inputs, that's the situation in which my proof applies, and I can show that the problem I want to set up is indeed going to be NP hard. But two inputs is like not kind of special. Of course, you could have a neural network with one input. I think I just figured out earlier today that for like a different reason that's not quite as interesting, that's also still going to be hard. That's still going to be NP hard to compute it in that case. Another situation you might consider is that this network doesn't have any biases, but if you had one input and biases on each of the hidden units, then it would still be NP hard. That would be like the same problem fundamentally as if you had two inputs and no biases. So yeah, in summary, this proof that I'm going to present to you about works as long as you have one input and one bias, or two inputs. And if you had fewer than that, if you had one input and no bias, or if you had bias and no input weights, like if all of these edges had weight 1 and you just had variable biases or something, that would still be NP complete, but I'm not going to show that. Any questions about the model? Okay, well, I need one more thing on this slide. I need to label these edges because we're going to need to refer to them. I'm going to label the output ones A1, A2, all the way through to AM. And the input ones, I'm going to label these two inputs coming into unit 1 are going to be B1, which is a vector in R2. And then this is going to be B2, and this is going to be Bn, which is also a vector in R2. So M vectors in R2 and M scalars, and that's a total of 3M parameters. Okay, so let's talk about compressing neural networks. So there are conditions under which it's possible to take a particular parameter and move around the units and rescale some of the weights to make the same function. Oh, I didn't talk about how this neural network implements a function, but the inputs and the outputs, I'm assuming most of you are familiar with this, and it matters that we're using the hyperbolic tangent activation function on the hidden units. So that's going to come up on this next slide. If you have a parameter, it might be that there's some way you can rearrange the weights and implement the same function. So what I mean is like for a particular w that is in our parameter space, then we've got a function fw, which looks something like this. It's the sum over all of the units of the output weight multiplied by the activation function hyperbolic tangent times the input weight vector in a product with the input vector. And this is a function from R2 to R. This function, maybe you can have some other w prime in R3M that gives you the same function, fw equals fw prime. In fact, maybe you can do it so that this w prime doesn't come from this parameter space, but some smaller parameter space. W prime prime, maybe R3M prime. There's a lot of primes and stuff, but I'm not committed to using these a lot, so I hope it won't get confusing. But just for now, maybe M prime is smaller than M. So you've got some network here that has fewer units, but it could still be the case that fw prime prime is equal to fw. So this is the condition called compressibility, and this is what I mean when I say you can take a network, you can take a neural network, you can like remove some of the units, you can compress it. And so let me define the rank of a function or a parameter. It doesn't really matter. Actually, just keep it simple, and I'll just say it's for a parameter. The rank of a parameter, and that parameter is in some sort of ambient architecture with m hidden units. This is the smallest m prime, the smallest m prime for which we could still implement the same function. So it's the minimum of m such that there exists some parameter in, I better make this m prime, R3m prime, such that fw prime is equal to fw. So I hope it's clear what I've said here, although I think the notation is not super clear, but hopefully what I'm saying is clear. It's how far can you compress this neural network? How many units do you really need to implement it at a minimum? So any questions about this definition? This is pretty fundamental. Okay, assuming this is clear, I'll go and tell you the different ways in which you can compute the rank of a parameter. So a lemma that comes kind of indirectly from Hector Sussman in 1992. And this is sort of a modified version, but that's because we're not considering biases. We've got a slightly different setting, but I'll just give you this version. So let me see. W in this architecture with m hidden units has full rank. So rank m out of m. M is like the maximum possible it could be, because we know that you can implement this neural network with m units by definition. So the question is whether or not you can do it with smaller. So we say you can't do it with fewer units if and only if you have these three conditions, 1 and 2 and 3. where one is no AI is equal to 0, where these are the outgoing weights of the parameter W. Intuitively, if any of the AIs were equal to 0, then you could just remove that unit because it's not contributing to the output. The second condition is no BI is equal to 0, 0. Remembering these are vectors in R2. Intuitively, if one of the BIs was 0, 0, what that would mean is you have a unit that doesn't receive any input, and so it becomes tan h of 0x, which is just 0. So this doesn't contribute to the output no matter what A you multiply it by. It doesn't contribute to the output, sorry. And finally, 3 is no pair of BI BJ has either BI equal to BJ nor BI equal to minus BJ. So I could just use absolute values if we were talking about scalars, but these, remember, these are vectors in R2. So you can imagine if they were like the lexicographic absolute value should not match for these input vectors. Intuitively, if you have two units that have the same input weight vectors, that means they are going to have the same output. And so you could combine them into a single unit that by pooling together the A values. And the same is true in the negative case because tan h is an odd function. So you can just take this negative through the tan h and then deal with the case as I just described. Any questions about this step? Okay. The next step is, yeah, was there a question?
I know, I'm saying no question.
Okay, thanks. The next step is to basically compute the rank. What we want to do is sort of iterate this. Well, we want to negate this theorem. First of all, to say that, you know, it's a corollary of this that if you meet any of these conditions, if you break any of these conditions, then, because it's an if and only if, then you don't have rank M, you must have lower rank. But these conditions, like I've kind of already described, they tell you how you could reduce the size of the network by eliminating units. So an algorithm for computing the rank goes something like this. Algorithm for computing the rank of W. It goes something like while W breaks conditions 1, 2, or 3, then reduce the size of W by sort of exploiting that that way that it breaks the condition. As discussed, I'll say. And by the end of this algorithm, the final W that you end up with, when you get out of this loop, it must not break any of the conditions, so it must have rank M. But every time you reduce the size, you've been decreasing M. So you just return. I don't know how to write. I don't have the notation here to say the number of units that are left in W, but I guess I'll just write that. The number of units. That's the rank. So this is my algorithm for finding the rank. So the lemma comes from Sussman, and I've just turned that into an algorithm by repeatedly applying it. Okay, so parametric approximate rank is the next step. So if you have a close look at these conditions, you'll notice that they all carve out a plane in the parameter space, a hyperplane in the parameter space. They're very sort of fragile conditions. If you just perturb any of the parameters, you'll probably let me get this right. I've got this sort of backwards. So if you're reducible, if you have a rank lower than m, and then you perturb the parameter, you will probably stop having a rank lower than m and go back to having a rank of m. So for example, if you had one of your AI values equal to 0, and then a perturbation will destroy that property, and you'll go back to having that AI value have a non-zero value. So the generic case is that you have rank m. But we can start to ask, well, are you all but a perturbation away from having a lower rank? And that motivates the definition of parametric approximate rank. Parametric because we're considering perturbations in parameter space. It's also possible to consider perturbations in function space, and then you would get functional approximate rank, which I'm also studying. But for today, parametric approximate rank. I'm going to call this the prank with a epsilon of w. This is equal to the minimum exact rank of w prime in a neighborhood of w. And I'm going to use a L infinity neighborhood because that's going to make things a little bit easier later when it comes to coming up with an algorithm for this. So this is w prime is within epsilon of w. So it's something like this, where we've got the parameter space. Okay, these things are just annoying. I thought they were really cool when I got them, but now I'm just a little bit over them. Anyway, this is R3M. Yeah, this is R3M. For conceptual illustrations, it might make sense to consider the axes to be like the low rank points, because that's where like maybe AI or BI is equal to 0 or something like that. So I could consider, we've got a point W here. We consider this L infinity neighborhood, and we look for the lowest rank parameter within this neighborhood. And in this case, if we buy the axes are low rank and the rest is the generic case of being full rank, the prank of this is the radius epsilon. The prank of W here is just m. But maybe if we consider this other example, a different color, W prime, and then we consider a neighborhood there, we might catch this axis, and then it would be the case that there's a point with low rank within this neighborhood. That means that the parametric approximate rank of W prime would be less than m. So that's the setup. And a natural question then is, okay, we've got an algorithm for computing the rank. Can we have an algorithm for computing the parametric approximate rank for a given parameter, a given epsilon, an ambient parameter space? That all matters in general. This is, yeah, that stuff all matters. Can we have an algorithm for this? So actually going all right for time. Yeah, we'll move on to now discussing this from a complexity theory perspective. So I'm going to define a problem which corresponds to computing the parametric approximate rank. I'm going to then try and state the theorem that it's NP complete, this problem, and sort of discuss what that means. And then we can discuss what this means for learning in neural networks. or we can go on to the proof, or we can sketch the proof, and we can do that sort of stuff. But first, I need to make sure that everyone's following me so far. So yeah, any questions about parametric approximate rank? All right.
I'm confused with this picture. Can you explain it again? So
yeah. Anything in particular is unclear?
So the x-axis you represent for like R3M. Well, what's your like y-axis for this?
Sorry, I guess I just mean the whole axis, the whole space is R3M, and
okay.
So yeah, that's more like everything.
I see. Then for this L infinity norm, the neighborhood of this W shouldn't be.
Sorry, my lag. This is the subnorm, so it's the max of all the components. And so it's definitely this kind of square shape.
I see, yeah.
I mean, okay, yeah, in R3M, for M interesting, it's going to be a hypercube.
Yeah.
Is that clear? Any other questions? Or so I can actually, you asked me to explain it again. I can try explaining it again as well. Let me know.
Yeah, I think that's good.
Okay, cool.
Thanks.
All right, let's move on to some computational complexity. So I'll write down the problem, and then I'll state the theorem, and then I'll quickly write down another version of the problem and state another theorem, which is the one I'm actually going to prove. This is like a wrapper around the problem. So the interesting one is the one that I'm about to write down. So problem. This is like a complexity theory definition. So in computer science, a problem is like a contract that you have to say, well, these are my inputs, what are my outputs? And then you would write an algorithm and you would prove that your algorithm for all inputs gives you the desired outputs. So in my case, this is the problem of, I'm going to call this problem PAR for parametric approximate rank. And I'm going to talk about I'm going to talk about a variant of this problem in which the input is some n, which is just a natural number, some w, which is in the parameter space for that m, and that's the input. The sort of desired output. Oh yeah, also we should actually have epsilon, which is just a positive real number. And the output is going to be the parametric approximate rank of with epsilon as the radius and w as the input. And this is defined according to the other board. So you've got to somehow find this minimum, or at least the rank of this minimum rank nearby parameter. And a theorem is that the problem PAR is in the complexity class NP hard. And what this means is that if you can solve this problem, you could use the solution to solve any problem in NP. But NP hard, you might have expected me to write NP complete. The difference is that NP complete problems are NP hard, and then they are also themselves in NP. So this is kind of like a greater than or equal to in difficulty and my theorem is that parametric approximate rank is at least as hard as the hardest problems in NP. But NP complete would be saying it's exactly as hard as the hardest problems in NP. The problem with this, the issue is that this problem, as I've stated it, is not a decision problem because the output isn't binary, it's not yes or no. And so this problem is not really eligible to be in NP. And so it's like a technicality why this isn't NP complete. But I do want to show you that a problem is NP complete, and this is the one I'm going to do. So I'm going to write a variant problem.
Oh, a quick question before you move on.
Yep.
Can you hear me?
Yeah.
Cool. So did you mention the complexity class of the original problem, not the P rank, but the original rank? You gave an algorithm, but is that like an effective algorithm?
It's a polynomial time algorithm there.
Cool.
Yeah.
Awesome. Thanks.
Yeah, it's super simple. You just have to basically, well, you could just iterate. You could just go through the whole parameter looking for a place where it breaks that condition, and that's like
of course. Yeah, of course. Yeah. I just thought about it. Yeah. Okay.
And
thanks.
you just iterate that. But there might be like faster ways to do it, but it doesn't matter. Yeah, it's certainly polynomial. Okay. Anyway, in this case, I'm going to tell you about a decision variant of the problem of parametric approximate rank. So this is like parametric approximate rank, but it's a decision problem. So the output is going to be yes or no. The input is the same. You've got your M, your W, and your epsilon. But actually, you also have an R, which is a sort of maximum rank. And the output is you take this. You have to tell me whether or not the parametric approximate rank is at most R. So this is a question I can answer with yes or no. So this is a decision problem. And you can see that that if you could compute the parametric approximate rank, then you could answer this problem. So that's the decision variant is possibly easier than parametric approximate rank, computing the actual parametric approximate rank. Because if you compute the parametric approximate rank, you could just do it, and then you could compare it to R, and then you could tell me the answer to the decision variant. And so the theorem that I'm actually going to show you is that this problem is NP complete. So we're now up to the statement. So I'll pause for questions about this slide. I know we've stepped into a little bit of complexity theory. So if this NP hard, NP complete stuff, I could do a better job explaining that, let me know. It'll also get to more details on it.
Maybe it's worth commenting that here NP means non-deterministic polynomial time with the relevant integer being the M, right? You could imagine that it was something to do with the amount of information used to specify epsilon or something, right? But the relevant scaling quantity is the M.
Yeah, that's true. It's the M. Sorry, I just need one moment to sort that out. I'll be back in a minute. Okay. Yeah, hopefully a couple of people are enthusiastic about my talk. All right. Yes, that's true. So this NP in this case is, the relevant parameter is M. Good point. Were there any questions? Okay. Then we're at a choice point. So what we could do now is talk a little bit about the kind of implications of this theorem. I could give a brief introduction to the kind of methodology whereby, like how, in complexity theory, how you prove something like this is NP-complete, and how I'm going to do it. And then I could sketch the proof in this specific case. Yeah, those are the two things we could move on to next. Any preferences?
I think given we have time, we should get into the proof and talk about interpretation some other time.
All right, cool. Then let's, I'll give you a kind of primer on the methodology here. So, so if you want to show that something is NP-complete, hopefully the noise is acceptable. NP-complete. A formal definition of this is something like, if you have access to one run of a NP-complete problems algorithm, then using the output of that, you could solve any NP problem in polynomial time, like deterministically you can do it. A kind of rough way to say it, which I think might be equivalent, or maybe it's sort of subtly not, but I think it's fine for our purposes, is if you have a polynomial time algorithm for an NP-complete problem, then you can use that as like you can use that algorithm to solve any problem in NP in polynomial time. So P would equal NP. And if you I am assuming throughout this like background familiarity with P equals NP, the P equals NP question, which is an open question in computational complexity theory and mathematics, and widely considered to be unlikely. It would be a huge surprise to many in the field if it was found that P is equal to NP. So what that means is that NP-complete problems probably don't have polynomial time algorithms, and that's the sense in which they're considered to be hard. But anyway, I strayed a little bit into the interpretation. What I meant to be saying is what it means for something to be NP-complete is you can use this. Let me write it like this. NP-complete problem means that you can use an algorithm for this problem to solve any NP problem. The starting point in complexity theory is that Boolean satisfiability meets this description. If you can solve satisfiability in polynomial time, you can show that you can use that. You can set up a propositional formula that kind of encodes the execution of a non-deterministic Turing machine that has a polynomial amount of kind of runtime, and then you get a polynomial size formula, and you can, if the formula is satisfiable, the Turing machine accepts. So you can use your SAT solver to solve any NP problem, which is NP problems are defined by by running in polynomial time on a non-deterministic Turing machine. So this is the first step. The next step is to say that, okay, so satisfiability, there are lots of Boolean formulas and some of them are quite complicated. It turns out that actually the kind of essence of most of these formulas is not so complicated. You can rearrange things, introduce new auxiliary variables, do some transformations, all of which is polynomial time, and get an instance of what's called 3SAT, which is a Boolean satisfiability. It's a logical formula with in conjunctive normal form. So it's a list of clauses that are conjoined together, so ands of clauses. And each clause is a disjunction of literals. And those literals are just propositional variables or negated propositional variables. So it's a very simple form. And moreover, each clause has at most 3 literals. So the clauses are kind of short, but there may be many variables. It turns out that if you can somehow solve this, you can use that to solve any arbitrary formula. So we've got another arrow there. The chain goes on, and this is the chain that I'm kind of going to invoke in my proof. If the 3 satisfiability formula not only has at most 3 literals per clause, but at most 3 occurrences per variable. So this is, I'll write that down because the notation's a little bit arcane. This is at most 3 literals per clause. And 3 sat with 3 with the overbar is also at most 3 appearances of each variable in any clause. That's another restricted form that you can also, if you could solve that, you could use it to solve any 3-sat instance and then any sat instance and then any NP complete problem. Sorry, any NP problem. One more restriction we're going to use is to 3-sat 3 with a planar clause variable incidence graph. So what this looks like is if you set up all of the variables, x1, x2, x3, and the clauses, clause 1, clause 2, and let's say clause 1 involves variables x1 and x2, you're going to put some edges there. Maybe some of these are negated occurrences. And clause 2 maybe contains all 3 variables. One of them is negated. This one comes around here. This graph that you end up with when you construct this graph that relates variables to the clauses they appear in, it has to be a planar graph. Of course, it's possible, this example is planar, but it's possible that you end up with something that's not planar, and that would be that would not be an instance of this restriction. But anyway, there's a proof that says that these problems are still hard. This restriction doesn't make it any easier. If you could solve it for any planar graph, you could still solve it for any non-planar graph, and then so on and so forth along these arrows all the way up to NP problems. One more step, or kind of 1.5 more steps. My contribution is to come in at the end here and say, if you could solve a problem that I define, which I'm going to call uniform point covering, if you could solve this problem, then you could solve planar 3-sat 3. And if you can solve that, then you can do parametric approximate rank decision variant.
I think you misspoke. If you can solve PAR, then you can solve uniform point covering, you mean?
Yeah, sorry, that's what I meant. If you can solve parametric approximate rank, you can solve uniform point covering. Therefore, you can solve planar 3-sat 3, you can solve 3-sat 3, 3-sat, sat, and then any NP problem by following this chain of reductions. And so my proof is to take, as stated in the and proved elsewhere in the literature, everything in white here, and to add the green stuff. And the reason that I introduced this new problem, we don't have to get into it. I think I'll probably just do a straight up sketch of the proof that doesn't go by this. But I think if we had time, it would. Uniform point covering seems like a kind of interesting problem in its own right, and it's like a way of factoring the proof that separates some of the different ideas that are going on into 2 separate things. Any questions about complexity theory?
So a question, you also do the reverse, right? You have to show that planar 3-sat also can solve PAR?
Yes, technically I do have to do that because I said I want to do NP complete, but I don't do it like that. What I say is that parametric approximate rank decision variant is in NP, and then I use this, if you like, to show that you could do it with planar 3 sat 3. So I go like the long way around.
Oh, I see.
Get back
Got
to
it.
this.
Oh, I see. Cool.
I guess it's not normally the super interesting part of the proof to show that the problem is NP, but this problem on that previous board is NP because you could basically just guess if you know about NP, a sufficient condition for being an NP, or actually it's an equivalent condition, is that there's some kind of lucky algorithm that starts with like a guess of polynomial size, and then is able to, if it is possible to guess right, you can then always get the right answer. And in this case, you just guess the reduced parameter. You just guess the W prime. You compute its rank. You check that it's lower than R, and that turns out to be an algorithm on a non-deterministic Turing machine that will compute the parametric approximate rank. Decision variant actually will decide the parametric approximate rank question. But yeah, the interesting part is the other direction, very much. Okay. What remains in the proof is to actually show this reduction, and I think I won't get too far derailed if I just skip uniform point covering and go straight to planar 3 sat 3. I'm going to show you the reduction, which is basically what I need to prove. I'll move on to the next board and write this down. So the theorem that I want to show is a reduction. Parametric approximate rank decision variant, I'm going to stop writing decision variant, is at least as hard as planar 3 sat 3. And the translation of this is, what this inequality here means is that for every instance of planar 3 sat 3, I can produce an equivalent instance of the parametric approximate rank problem. And where equivalent means that if I solve the first problem, if I solve the parametric approximate rank problem, it would have the same answer as solving the planar 3 sat 3 problem. So what I have to do is that for all instances of planar 3 sat 3, there exists instance. I'm going to introduce some letters here. This is an instance X, and this is going to be an instance Y of parametric approximate rank decision variant, such that the parametric approximate rank answer of Y is equal to the planar 3 sat 3 answer. That's not super clear. What I mean is that this instance has a parametric approximate rank less than or equal to its respective R, if and only if the planar 3 sat 3 formula that we started with is satisfiable. That's right. This is a formula, and this is a neural network parameter, but also an epsilon and an R. All three of those things. And an M actually, but it's part of the parameter implicitly. So this is my job, is to show you how to turn a formula into a parametric approximate rank instance, such that the parametric approximate rank instance works out to be just so compressible as the planar 3 sat 3 instance. Is satisfiable. Is that clear? All right, let's go. In less than 10 minutes. I will sketch the proof. I obviously won't go through it in full detail. Maybe by way of an example, I think will be the clearest. I'm going to start with a planar clause incidence graph. Let me just find the exact graph that I want to use that I have prepared earlier, which is here. It is similar to the one we talked about before. We're going to have 3 clauses and 3 variables. Because it's a planar graph and it's going to revolve around that, I'm not going to write it out in logical notation. I'm just going to jump straight to this version. So we have a negated, clause 1 is not x1 or x2, where this is negation. Clause 2 is x2 or x3, and clause 3 is x1 or not x2 or not x3. This is a very simple formula and it's satisfiable, completely easily satisfiable. The first step of the reduction is to take this formula and embed it into a grid. Take this graph, embed it into a grid. The best embedding you can do for this one is something like C1, X1, that's a negated edge, X2, that's not negated, X2 also appears in clause 2. It's going to end up looking like this. Just fill in the details. This is clause 3. This is a negation. This is a negation. This is X3. Yeah, so I put this on a grid. I have to care about this because all I know is the graph is planar. I don't know a priori that I can put it in this layout, but there's a theorem from somewhere else that says that you can always do this, and you end up with a polynomial size grid for your planar graph. So I can do that. Okay, the next step is to turn this into a neural network parameter somehow. My plan is going to be to kind of take each component of this grid and turn it into like a. Let me explain this. Yeah, I'm gonna conceptually think of this as a system of tiles that looks something like this. So there's actually like a void of space here and here, and you can see that this grid maps onto this this sort of funny tile arrangement, such that like this is clause 3, for example. Yeah. And what I'm going to do is for each of these tiles, I'm going to actually embed a series of points into the plane that are going to look something like this. I don't remember the exact arrangement off the top of my head. I have to look that up when I get into detail, but there's going to be an arrangement of points that corresponds to variable x1. There's going to be an arrangement of points that corresponds to each of these edges. There's going to be an arrangement of points that corresponds to each clause. And those points, this is how I'm going to sort of systematically construct a set of B vectors. So each point is going to be a B vector of a hidden unit in a neural network. Now, parametric approximate rank corresponds to kind of finding ways to approximately combine units in the network to reduce the size of the network. If we remember back to those conditions with which you can reduce the rank on the earlier slide, what we can do is we can rule out using conditions 1 and 2 we can rule out using conditions 1 and 2 by putting these points far away from the axes. So none of the AIs are going to be anywhere near 0. None of the BIs are going to be anywhere near the origin either. And then the only way that you can think of this network that we're going to build as having a nearby parameter of low rank is if there's some way to kind of combine there's going to be some way to combine the parameters, the b values, by perturbing them to sort of merge them into each other. So I'll take an example of if I want to set up one of these edges. I want to make it so that I have a point here that corresponds to the tile. There's a tile down here that corresponds to x1. I'm sort of zooming in on this part of the picture. Then I want to have a series of points here that correspond to this edge. And then I want to have a set of points here that corresponds to this. Remember, actually that's wrong. It's like this. This clause. It's getting a little messy, but the idea is going to be that if you look at these 4 points, if you decide to merge these units and these units, which will turn out to be within the tolerance, the epsilon for doing so, you can set that up. That's one option. Another option would be that you choose these points and these points, but then with the same number of units, you don't get to cover this one as well. That would cost you extra. Basically, we can sort of set up the system of points so that when you make choices down here about how to cover the points, it's gonna flow through to whether or not you can cover this wire like this or the other way. If you can cover it like this, that's going to flow through the clause, which is going to determine whether or not you can cover all the points in the clause. And the upshot is that if you carefully set up the system of points, you can set it up so that you're going to be able to cover it. You give it some budget of units. You're going to be able to merge the units in such a way only if and only if there's a satisfying assignment to the formula. Because if there is a satisfying assignment of the formula, you can use that to just to make the decisions about how to do the covering, to use less, use less groups. And if there is a way to do it with less groups, you can show that that must be because there's a satisfying assignment, because if there wasn't a satisfying assignment, there would just be no way fundamentally to cover it with a certain budget. So there's a lot of details, and obviously we're out of time to discuss all of them, but that could be I'm totally happy to do that as a topic of a future discussion where we go through all of these details. Any questions? Yeah. Well, okay, it's a standard thing in the sense that almost all complexity reductions involve what's called gadgets. This is a very standard methodology in this field where you build kind of pieces that represent the different elements of the, in this case, the satisfiability problem. You build pieces that correspond to those in their behavior, and then you build your instance out of you let the SAT instance act as a blueprint for your problem instance, where you just compose the pieces in the right way. That is a totally standard methodology for this area. This tile thing, I haven't specifically seen building a circuit into a grid and then using tiles as the gadgets. But I'm sure it's, if people aren't thinking about it in terms of tiles, they're certainly doing a very similar thing when they do these kinds of proofs for the NP completeness of like k-means in the plane and that kind of thing. But I haven't spent a lot of time looking at that literature, so I guess I can claim that at least I've independently found this particular thing, even if it has been done before.
So how do you think about this problem and the significance of its difficulty? So why would I want to compute approximate rank? What's wrong with rank? Rank seems good. That's easy. Why don't I just compute that?
Well, that's a great question, and obviously we've talked about this. Like I sort of hinted at before, in the generic case, a parameter is going to be full rank. If not for like numerical reasons, like reasons of numerical precision, in an implementation, if you were learning a neural network, and you have some floating point representation of it, it is probably not going to be the case that the A values are exactly 0, but they might be close to 0. And you might want some way to kind of relax the kind of numerically precise definition, which is this rank. And one way to do that is to consider parametric approximate rank by allowing yourself to kind of perturb these parameters independently and see if you can find a network that has low rank in terms of like exact rank. So that's why we might need approximate rank rather than exact rank. And it would be nice to have a measure of rank because I think that, well, one motivation, for example, is that if you want to think about how complex your neural network is, the number of units is probably not a very good indication because there might be this kind of redundancy where if you really tried, you could implement the same function or a very similar function with many fewer units if you looked for ways that you could kind of economize on units. And so I think that could be an interesting way well, one way to measure that is by this definition of rank as a measure of complexity of neural networks. And I don't think that's been done before, although there are other measures in the literature of the kind of effective dimensionality of a neural network. I don't think this one has been proposed before. And another motivation, I guess maybe Dan would be better placed to articulate it, is that there's some chance that a Bayesian interpretation of deep learning involves kind of a special role for these networks. Oh yeah, the singular learning theory interpretation is that when you have a rank that is not a full rank, that is the situation where you have a singular Fisher information matrix in the parameter space. So it's a theorem that if rank is less than m, then if the rank of W is less than m, then the Fisher information matrix at W is singular. For 10H networks, the converse is also true, but not for value networks. But yeah, so these are kind of the singularities that we think are important in learning, and it would be interesting to measure, like, are we near one of those?
Yeah, let me add to that a little and then poke Edmund in the side to see if he says anything. So we expect, if we're trying to learn a true distribution from data samples, the learning process will maybe get close to the set of true parameters, and the set of true parameters may be made up of highly degenerate networks, that is, those with low rank. Then there's the question of, okay, I learned my parameter. It's probably not going to be exactly a true parameter, but it's near that set. So I'm sitting at some W which is close to this complicated set of degenerate networks. And then I can ask the question, well, how close am I? And what does it look like near me? What does my neighborhood look like? And one of the very simplest questions that you might, in that direction formally, is, well, if I take a little epsilon neighborhood of my parameter, what kind of degenerate networks are there? And that corresponds to the geometry of the set of true parameters, right? Which is has various components, and those components are made up of different ways of being degenerate. So you imagine a bunch of planes meeting each other, for example. Spencer's thesis has some nice pictures that show that. So you imagine a configuration of planes or other hypersurfaces meeting in some complicated way, and then you're sitting near one of those complicated intersections, and you just ask the question, well, am I closer to a plane or am I closer to where two planes meet? Those correspond to networks with different degrees of degeneracy. And what Matt's explaining is that if you try and answer that question, you're facing essentially a complicated satisfiability problem. I mean, in the tiles here, to merge these 2 points corresponds to moving from your W towards one of those intersections of planes. But maybe there's a closer thing you could go to, which corresponds to merging these points in some other way. So these ways of merging these points correspond to paths through parameter space towards the set of true parameters, this complicated geometric object. So exploring your neighborhood is related to these collapsing these points, and this is a complicated problem, which in some sense means the geometry is complicated, although I don't know exactly how to formally say geometry is complicated, I guess. But that's how I interpret this. Okay, Edmund Poke.
Right. Yeah, I fully agree with what you're saying, and I think it's I guess a way I will put it is there's two sources or reason we will want to consider neighborhood of a network, neighborhood of a parameter, be it true or not. Which is one source is that, as Dan said, we are talking about Bayesian averaging in a neighborhood. Like the performance, in some sense, the performance of a neighborhood is the performance of a Bayesian predictive distribution restricted to a neighborhood is not about the lowest point. It's about the neighborhood. The other source is the fact that we don't really know. We don't have access to the true parameter. We only have access to the data, and for finite number of data, there are lots of solution that looks equally likely, and even if generically the true parameter is full rank, let's say, the data might make it look like the non-full rank one is better. The two sources, one is we are talking about averaging averaging parameter in the neighborhood, and the other one is that we have ambiguity because we only can plot the true parameter via data, by a number of data.